Hi, everybody. It's my pleasure to introduce Marla Geha for the benefit of the people that have not been at our workshop. Marla has been faculty at Yale, which is where she went after having an extended postdoc here in Pasadena at Carnegie, and after her PhD at Santa Cruz, which is where she started working on these rather insubstantial seeming galaxies at the time, dwarf galaxies, which have ended up having a much greater impact than many people could have guessed back in the early days. And we're very excited to have Marla talk to us about the darkest galaxies. Marla.
I think you're supposed to do that after. Yeah. Thank you very much. It's a pleasure to talk here today. The conference in the last week and a half has been really interesting, and I want to thank both Lexi and Andrew for organizing, and Michelle Judd as well for making it an amazingly smooth meeting. So in the past 4 years, so well after I finished my PhD, the number of satellites around the Milky Way has almost doubled, more than doubled. And all these new objects turn out to be really remarkable for several different reasons. They turn out to be the least luminous galaxies that we know of. They turn out to be the most dark matter-dominated galaxies. They also turn out to be the least chemically enriched galaxies. And so for a number of different reasons, they are really amazing probes, both of galaxy formation, cosmology, as well as dark matter. And so what I will do today is both explain why I'm giving a talk on objects with 4 or 5 years ago I would have argued fairly vigorously didn't exist, why we missed them and how they were found, why we think that the masses that we're estimating are correct, and that's really the bulk of the talk, is trying to convince you that we know what we're doing in some sense, which is convincing ourselves as well. Once we've established that these objects are in fact galaxies and are in fact dark matter dominated, then use them as probes of dark matter and cosmology and that sort of thing. So my collaborators here, many of whom are in the room and are welcome to correct me or anything that I do wrong. So just to get everyone on the same page, the word dwarf galaxy is used, I'll use throughout the talk, but really represents a huge range of properties in galaxies. And so I just kind of wanted to go through that. Dwarf galaxies, that word is used for anything that has an absolute magnitude less than about -18, fainter than -18, which corresponds to something that's roughly a tenth of the Milky Way mass or are less massive. Dwarfs come in two varieties, just like big galaxies, those with and without gas. The objects that I'm talking about today, largely with one exception, have no gas, and the limits on their gas content are actually fairly extreme. Segue 1, which is something I'll be talking about a lot, has a gas mass at most 10 solar masses of H1, which is really a pretty remarkable limit. On the scale of these objects, so these are two of the brighter dwarf galaxies in the local group, if we put the Milky Way on here, it would take up sort of most of this wall. In comparison, things that are a bit fainter, something like Leo 1, these are the classical satellites that we knew of before 2004, down at sort of -12. And the objects I'm talking about today, scaling just with radius, are things like this. So really, really remarkably small and very, very low luminosities. And here I'll be using the word ultra-faint for obvious reasons. So in the context of this workshop and in terms of dark matter, dwarf galaxies have multiple different uses in terms of constraining what we understand about cosmology and dark matter. Really the simplest one is simply by counting up the number of dwarf galaxies. And so in this picture of hierarchical galaxy formation, dwarf galaxies are the lowest mass objects, and they're the ones to collapse first, and then merge and hierarchically form larger and larger structures. And so here is the simulation. In the simulations, the details in this don't matter, and I don't want you to worry about the details. This is a CDM simulation of the structure of gas at fairly high redshift. And in comparison, and using sort of a similar initial conditions, this is a warm dark matter simulation. So that is, the dark matter particle has a little bit more energy and basically stirs up the small-scale structure and smooths it over. And so you can sort of see the large-scale structure in both of these simulations is similar, but the small-scale structure is extremely different. And so if we just go and circle where galaxies will form at redshift 0, you can see that the two simulations predict very, very different numbers for the relative numbers of dwarf galaxies versus massive galaxies. And so if we can just go out and count all the small galaxies and compare them to the big galaxies, we should have some constraint on whether dark matter, what the mass of the dark matter particle actually is. And this turns out to be fairly difficult, although it seems straightforward. If we counted up 5 years ago the number of dwarf galaxies in the Milky Way and compared that to the number of dwarfs we would expect around a simulated Milky Way, the numbers were very, very different, and this is the missing satellite problem that we talk about fairly often. Where different is we had 11 galaxies, satellite galaxies, and cosmological predictions were suggesting more like a few hundred. And so just simply counting the number provides a strong constraint. It turns out we're actually fairly bad at counting galaxies. And I'll show you that in a second. So this is an all-sky projection showing where the dwarfs in the Milky Way were before, that we knew before 2005 or so. The last galaxy was Sagittarius that was discovered in 1994. And so if we just did a census of satellites around the Milky Way, there would be 11 before 2004. Now, if we did some updated census survey in 2009, we've had a whole new population of objects that have been added up to even just a couple of months ago. And there are now 14 new galaxies around the Milky Way, bringing the total up to 25. All the new galaxies, all these red things you'll notice are up in the top part of the plot. The gray region in this plot is all the SDSS Sloan Digital Sky Survey coverage. All of the new objects have been found in the Sloan Digital Sky Survey. And so where most of the coverage is in the northern hemisphere, that's where all of the dwarfs have been found so far. And so, obviously, we have some incompleteness in our census data, as all census data tend to have. And if we just sort of were able to get a full sky Sloan survey, so Sloan covers about a quarter of the sky, if we're able to do the full sky, we would obviously expect this census to go up. And so that's quantified in this plot by Eric Tollerad, who's a graduate student at UC Irvine. So plotting... Great. So plotting the absolute magnitude on the x-axis, where bright is up here and faint is over here. The red points are all the galaxies, the satellite galaxies that we know of today, so that 25. And then the green and blue are various different extrapolations of our incompleteness. So if we just assume that the Sloan Digital Sky Survey covered a fourth of the sky, and if it covers the rest of the sky and things are homogeneous, we would expect the total number of satellites to be somewhere around 50 to 70, depending on sort of small number statistics. However, Sloan Digital Sky Survey has a magnitude limit, and that magnitude limit prevents us from finding the faintest galaxies out to large radius. And so that's where this blue curve comes in, and that's where the incompleteness correction is really quite uncertain. So we have to assume some sort of radial distribution for the faintest satellites. And if we assume some sort of distribution coming out of simulations, there should be up to something like a few hundred satellites around the Milky Way. And so in terms of discovery space, we have a huge way to go from 25 up to something like 500. So expect a lot more discoveries in the next couple of years. These least luminous, so where the incompleteness correction is the worst, also turn out to be the most interesting in terms of a broader perspective. So these least luminous satellites turn out to be particularly useful for multiple different reasons. From galaxy formation, as I mentioned, because they really are some of the highest mass-to-light ratios, as I'll show. From cosmology, both the luminosity function and the mass function gives us a real test of CDM, and this is the missing satellite problem, as well as particle physics. So these are also quite interesting in terms of indirect detections, and I'll go through all of this towards the end of the talk. But first, we actually have to believe that these objects are, in fact, galaxies. I didn't know where to put this in, so I just stuck this in. It doesn't quite fit. But I want to point out that these things are faint. And when I mean faint, I actually really mean faint. The faintest galaxy is Segue 1, has an total absolute magnitude of -1.5, which corresponds to their individual stars that have luminosity larger than the total luminosity of this galaxy. So this is just a color magnitude diagram with the absolute magnitude on this side. You can, the main sequence and giant stars. Segue 1 has an absolute magnitude of -1, which comes right here. So there's a handful of stars that are, in fact, brighter than the entire luminosity of this galaxy. It doesn't mean that it has very, very few stars. Most of the stars are very, very faint, and so not really contributing to the luminosity. That's just a side note. So why were these objects missed and how did we actually find them? And going through this kind of will give you an understanding of why these objects really are quite unique. So this is an image, again, of this faintest galaxy, Segue 1, and there is nothing to see in this image. With no amount of imagination can you see that there's a dwarf galaxy in this image that has a radius sort of right in the middle, about a quarter of the size of this image. And the problem here is that the Milky Way foreground is basically overwhelming the number of stars in Segue. So what we see, this galaxy is fairly close, so we resolve individual stars in this object. But most of the stars that you see in this image are actually foreground Milky Way. And so what we need to do is filter out the foreground Milky Way stars in order to bring up the dwarf galaxy, which is just slightly beyond in distance. And so to do that, I take all the stars and I just turn them into points. And then I apply some sort of filter to the data. And so I know if I have a dwarf galaxy sitting at a certain distance with a certain population, that all those stars should have a very unique pattern in color and magnitude. And so this is just an example of our filter. All the stars that have a color and a magnitude that fall in this filter we include, and everything else we get rid of. And then we step this filter at various different distances in order to try and find stars, try and find galaxies. And so in this case, these are all of the stars in this field. And if I apply this filter, again at a certain distance, I get rid of a fair number of them. And you can perhaps start to see that there's something going on in the center. And if I smooth this based on some size.
It looks like the filter is an isochrone.
Yes.
So you're taking somebody's stellar evolution model.
Yeah. So what we do, we have a fairly liberal cut in terms of what the color magnitude is. So it's an old population.
Obviously very low metallicity.
And low metallicity, although we do allow for a fairly large range. I think something -1 to -3. It's a very, very large range.
But way below the Milky Way.
But somewhat below the Milky Way, yes. But there are certainly biases in this search technique, and I'm going to stress that in a moment. So if we smooth this image or smooth this filtered image, you can see that there is in fact something there. There's an overdensity of stars, which for the moment just allow me to call a dwarf galaxy.
The RA and Deck are in degrees?
The RA and Deck in this case are in degrees. And so in all the search, I'll just jump ahead for a second then. In all of these searches, we have assumed a size. And basically, we've assumed a size when I did that filtering. That size tends to be on the order of a couple of arc minutes. And so there is a bias in the current dwarf galaxy sample against things that have similar luminosities but are larger, which translates into a bias in surface brightness. So there's a whole class, perhaps, of lower surface brightness galaxies that we have still missed. And it's the next generation of searches that will go there. So coming back to this image, and now taking out just the stars that belong to the galaxy that were in that overdensity. This is a fake image, but taking out just those stars. And you can see that the number of stars in this image is much, much lower, and you really wouldn't have been able to pick out that pattern in this image. And so the reason we missed these objects, that we missed all of them, is that although they have similar magnitudes to, let's say, a globular cluster, which you certainly can see in an image, they've just been stretched out in radius and have much, much lower surface brightnesses, which is why we missed them. And again, just to stress that biases remain both in size and in surface brightness, which really are linked. So now that we've found an overdensity of stars, it is not an obvious conclusion that this thing is, in fact, a galaxy. And in order to do that, we need to get velocities and measure their masses. And so, what are these overdensities? When Josh Simon and I first went to the telescope to try and these objects were published, these candidates were published, we went to the telescope to try and get velocities. I think, at least in my mind, I expected about half of them to be something else and not a real galaxy. I think that was, I think I maybe even bet on it. And so, the question is, are they dwarf galaxies or sort of strange globular clusters? In the context of the old idea of the Milky Way, where things are smooth and dwarf galaxies live in a smooth halo, those are really the two possibilities. In our more modern version of what a galaxy halo looks like, where we have stellar streams and dwarf galaxies coming in and merging and being ripped apart, there's a third possibility, and this is really what I expected, is that perhaps these overdensities are just two tidal streams that are crossing. And what we're seeing is an asterism, just something that's not gravitationally associated with each other, but just happen to be there spatially. And so in order to answer the question of what these things actually are, you really have to get kinematics as well as chemistries to be able to tell these various different things apart. Kinematics to be able to tell whether or not they're gravitationally bound, chemistries and chemical abundances to really distinguish these from something like a globular cluster. Okay, so how do we do that? The DEIMOS spectrograph on Keck has really been an instrumental instrument in all of this work. And the reason is that its spectral resolution is really well matched to this problem, and we were able to get many, many stars at a single go. So we get something like 150 stars in a single pointing, and the size of where we can put those, where we can get those velocities is well matched to the sizes of these dwarf galaxies. So in some sense, it's about as well designed an instrument for this problem as you could come up with. So the DEIMOS, we're working in the red from H alpha to about the calcium triplet. I'll just point out that the spectral resolution per pixel is about 12 kilometers a second. This is just a small portion of data where the stars are the vertical lines going upwards, and you're seeing about 20 stars there. The velocity dispersions of these dwarf galaxies are on the order of 5 to 8 kilometers a second. And so if our resolution, our per pixel resolution is 12 kilometers per pixel, we really have to do a very good job of measuring velocities. And that's where most of the bulk of the work is really trying to understand our errors and our error bar, systematic and random velocities. And we've done a lot of work there, and I'm very happy to talk about that afterwards if you're interested. So we get velocities for all the stars, and this is just an example of what we find. This is a velocity histogram where most of the stars between sort of minus 50 to 50 kilometers a second are Milky Way stars, foreground Milky Way stars. And you can see a very clear, cold peak in the velocity dispersion, which sort of broadly, we measure the dispersion, just the width in that peak, and estimate a mass for each object. But let's go into that in more detail. So here is for the same plot for 8 galaxies, 8 of these ultrafaint galaxies. And you can see in all cases, we do in fact see a peak, where we see a little bit of Milky Way and then a very, very clear peak in the velocities.
Now, the Milky Way stars, the ones you're calling Milky Way, they have low velocities. Those pass your color cut?
Yes. So, I mean, the Milky Way foreground stars, because they're basically at all distances or a range of distances, and so there absolutely will be contamination in the most perfect color sample that you can find, which is why the velocities and getting the abundances is crucial. So all of these have a fairly clear width in dispersion. So just plotting the velocity dispersion as a function of luminosity, and I wanted to plot this because this is really the simplest and the most straightforward, to me at least, evidence for dark matter. So here is just modeling the total luminosity, which we can measure fairly well from those images, as a function of their velocity dispersion. And so, these are the ultrafaints, these are the new galaxies, and the blue are the old classical galaxies. And the several plots beyond this all use the same color coding. And so, first of all, just note that there's a factor 10 to the 5 decrease in luminosity versus just a factor of 2 decrease in velocity dispersion. So that's sort of a hint that something interesting might be going on. And what I can do is let's say these objects are just stars. I can figure out what the mass of something that just has stars is and turn that into a velocity dispersion that I would expect. And so if I do that fairly roughly, this is where I would expect most of the velocity dispersions to be. So they're well below our 1 sigma error bars. And the velocity dispersions that we're measuring are factors of 5 or more above what we would expect from just the stars alone. And so that really, to me, is the very simplest evidence that there is dark matter in these objects. But let's get a little bit more sophisticated. So taking the dispersions here, and I can assume a very, very simple model. Let's say that mass follows light. We're getting mass-light ratios that are on the order of sort of 100 to 1,000, so implying a huge amount of non-baryonic dark matter. Let's see. So in order to really get the masses, I can assume a lot of various different things. I can assume mass follows light. I can assume some sort of density profile. And Joe Wolf and his advisors at UC Irvine have come up with a kind of an interesting, cute way to estimate the mass. So it turns out that the half-light radius, of an object is a very good place to measure the mass. And what happens, there's a problem, we have these velocities, they're all sort of 1D velocities, so we were measuring a potential based on sort of one component of the 3D space motion. And so there's a degeneracy between the slope of the density profile in a galaxy and the velocity anisotropy. Basically, we don't know what the 2D space motion is. We only have 1D of that. And so this degeneracy can really be a problem if we're trying to estimate masses at very different points. And assuming the Jeans equation in certain types of profiles, the half-light radius is a point where, in fact, these degeneracies are minimized. And so it's a great place to be able to measure the mass. And so here now I've converted all those velocity dispersions into the mass within the half-light radius. And so you can see the masses are decreasing as a function of the luminosity. And I can also do something similar in plotting the mass-to-light ratios. So the mass-to-light ratios as a function of luminosity are increasing quite rapidly. So the mass-to-light ratio is increasing with a function of luminosity. Let me skip this and I'll come back to it in a moment. So we're plotting the half mass radius, half the mass within the half-light radius. But that's a little bit perhaps not the right thing to do in the sense that we're measuring the mass within various different physical radius in each dwarf galaxy. And so in the least luminous galaxies, that mass is being measured within a very, very small physical radius. In the most luminous, it's being measured within a very, very large physical radius. And so Louis Strigari thought, well, what we really should be doing is kind of comparing more apples to apples and comparing within a fixed physical radius. And so this has now become a fairly famous plot, and we've showed it in this workshop multiple times. The same thing as a function of luminosity, but now plotting the mass within a fixed physical radius for each galaxy. And this fixed physical radius, 300 parsecs, was chosen sort of to minimize, for the least luminous ones, the region we have to extrapolate out because we don't have data, and the ones where we're getting rid of a lot of data. And so a similar plot could be made for M500 or M50 or M100 or something like that. And they all show fairly similar things, that the mass within this fixed physical radius is very similar across this huge range in luminosity. It says something about the average densities within these regions. So I'm going to come back to this plot towards the end of it. I promised Joe that I would show this plot. And this is a broader, this is just putting these mass-to-light ratios in some context. So now this is the same thing, mass-to-light ratio as a function, I guess this is now of mass, not luminosity, for everything. So for most stellar systems that we know of. So the blue and the red are still our dwarf galaxies with very, very high mass-to-light ratios. These objects here are globular clusters, so they don't have very much dark matter or any dark matter. Regular galaxies, the Milky Way is somewhere over here, going all the way up to galaxy clusters. And so I do think it's actually interesting that we think of galaxy clusters as being some of the most dark matter-dominated areas. In fact, the dwarf galaxies, the ultrafaints, are the most dark matter-dominated systems that we know. So this is kind of an interesting plot to really put everything in context. Okay, so I want to just, again, really focus on Segue 1 to really prove that we are measuring masses correctly and we haven't done something wrong. So I'll just show you the data for this object. So here is for Segue 1. This is, again, the same velocity histogram. This is the color magnitude diagram where now all these red stars we've identified as members. So we see that they're lying along the isochrone. And then the spatial distribution where I think the inner circle is the half-light radius, although I may, yeah. Let's see. So with 24 stars, we can estimate a mass, and these are the masses that we get. So from stars only, we would expect something like half a kilometer a second, and we're measuring more like 4.5 kilometers a second. So clearly, there's some dark matter going on. And doing the half-light rate, or the half-light M1/2, something like 10 to the 5th solar masses, and going out to M300 is more like 10 to the 7th. So there's some worry here that we're only measuring 24 stars and trying to estimate, what's going on in this gravitational potential. I didn't list it here. The distance of Segue 1 is only about 23 kiloparsecs, so it's actually fairly close to the Milky Way. And there's a real worry that perhaps the velocities that we're measuring are not tracing the gravitational potential, and the way that would happen is that if there's being some sort of tidal interactions or some sort of tidal disruption from the Milky Way. And so that was a real worry that we had, and with 24 stars, it's really difficult to say very much. Some evidence of tidal interactions might be, more stars out at larger radius than we might expect. Perhaps we'd see a little bit of shear or rotation or something like that. So to really try and test whether or not there's any sort of tidal disruption or evidence for tidal disruption, we went and got a lot more data, which is always nice. And just a couple of months ago, we have a complete sample of stars. So a complete sample of stars out to roughly 15 arc minutes, or it's more than 2 effective radius, actually, to down to our magnitude limit of about 22nd magnitude. So there really are no more stars down to the limit that Keck can do reasonably in this region. And so here are the new data, which are really quite remarkable. Let me just do that again, because it's really fun. So now you can see the red is now a model of what we expect for the Milky Way. So you can see that the number of Milky Way stars has really increased. We see that the peak near Segue 1 has increased quite a bit. I'll come and talk about this extra peak, come back to that in a moment. And you can see that the spatial distribution of stars, we've just started to sample what is definitely a centrally concentrated object. And so we're clearly seeing more stars in the center and less in the outside. And so it doesn't look like there's any evidence for this thing being tidally ripped apart, where we would have expected perhaps a lot more stars out in this region that were associated with Segue. Coming back to this other peak, there's been a paper in the literature, which I won't actually mention in name, claiming that Segue 1 is in fact tidally, that there's some inflation in our masses. And the argument here is that Segue is in fact superimposed on the Sagittarius stream, which is a well-known tidal stream. And we think that these stars in this extra peak are coming from Sagittarius. They're at a very, very different velocity. They have very, very different chemistries. And if I plotted their spatial distribution, they are not centrally concentrated. So they really are all over the place. And so we think that we can really well separate these Sagittarius stars from the Segue stars, both in velocity, position, and in chemistry. And so that this argument that the velocity dispersion of Segue is being inflated from contamination from Sagittarius, I don't think flies in the face of a lot more data. Showing a slide that Josh showed at the AAS meeting. So this is the same spatial distribution, now just reversing, going from black to white and white to black, just to confuse you. Again, the red are the Sagittarius stars, and we really don't see any obvious signs of tidal disruption. And so what we ask ourselves when we would try and find evidence is perhaps there's some sort of velocity gradient across this as done from the shear of the Milky Way across this. And we really don't see any evidence for that in our velocity dispersions.
You said the red are the Sagittarius stars. I think you meant to say Segue.
Oh, I certainly meant Segue, sorry. We don't really see an excess of stars at large radius that we expect perhaps if there was some sort of tidal tail being pulled off of this. And we certainly don't see the velocity dispersion increasing with radius, which again might be a sign of tidal disruption. And this is a really key point, that we see no evidence for tidal disruption. It does not mean that Segue is that Segue is not tidally disrupting. There are ways you can get models and that sort of thing where we would see something that looks bound that's not. But in the absence of evidence, we assume, oh, hey, come back. Sorry. In the absence of evidence, we assume that the stars, the velocities that we see, are faithfully chasing the gravitational potential. And that's something that is really key as we go on and use these things for dark matter studies. So I just want to, in contrast, show you a place where, in fact, the stars are probably not faithfully tracing the gravitational potential. And this is Willman 1. So Willman 1 was the first of these objects to be discovered, of these new ultrafaints to be discovered. Maybe it was the second, but I think it was the first. And has been sort of called the prototype of the ultrafaint class. And as all prototypes turn out, Willman 1 is probably not, in fact, a galaxy. And so here are the evidence. Beth Willman is putting a paper together on these data. It's really quite unsatisfying in that it's very difficult to say very much about this galaxy. So here, again, is the velocity histogram of Willman 1. And one real problem with this galaxy is that, unlike Segue, which is well removed in velocity space from the Milky Way foreground stars, Willman 1 is right in the middle of it. So the bulk of the Milky Way stars that we expect are between sort of minus 50 and 0 kilometers a second in this position of the sky, and Willman is sitting right in the middle of it. So it's very difficult just from velocity to distinguish between stars that are members of the galaxy and stars that are foreground. So let me take this velocity histogram and give you a little bit more information. So now I have velocity on the y-axis and distance away from the center, where the center is defined as what we see in the photometry. Red and blue are stars that pass our color and magnitude test. So they're lying on a very close in isochrones. And all the white objects are things that are fairly far away in color from Willman 1. And so you can start to see just, there's something funky going on in the center versus the sides. And so Beth has done a lot of tests, and it's very difficult to give you a conclusion. So let's say we use all of the stars, both the red and the blue stars. This is the systemic velocity and the dispersion. So first concentrate on just the blue line. So the blue line is using all of these stars, and you can see this sort of dip in the central velocity as you go up farther out in radius. And here is the dispersion as you go farther out in radius, and that's where the dispersion is being measured within some annulus. So at this point, you're measuring all the stars inside. So you can see we're getting velocity dispersions on the order of 4 or 5 kilometers a second, and we would conclude that this is a dwarf galaxy. Now, if we add the next piece of information in, and we now know what the chemistries of most of these stars are, we find that there are several stars that look like they're Willman 1 stars from velocity and from color and magnitude, but in fact have fairly high metallicities, suggesting that they are in fact foreground Milky Way stars. And so if we just get rid of these 5 stars, that gives you the red curve. And so this jump in velocity is now a little bit more extreme, and the velocity dispersion is equivalent to 0. I don't have a conclusion to say. This is maybe a stellar overdensity. Perhaps this is some kind of disrupted star cluster or a real star cluster, but it just doesn't seem to be as waterproof as Segue. And so this is for some of the people in the audience. Just please don't use this in dark matter studies, because it's just, if you have precious resources, like say some of the dark matter telescopes, the Air-Cherenkov telescopes, and you have precious amounts of observing time, this is not the place you want to go and invest those resources. And this paper will hopefully come out in the next couple of months, but you know how these things go. Okay, one other note in terms of understanding whether or not there's tidal disruption going on comes from the metallicities. There's a huge amount of information in the metallicities, and I am focusing on dark matter, and so I don't have time to go into it, but I really wanted to show this plot. Again, these are the classical satellites and the ultrafaints, function of luminosity, and now this is the inferred average metallicity in each object. And what you can see is that there's actually a fairly well-defined relationship between luminosity and metallicity in these objects. And this is consistent. There's a very well-known mass-metallicity relationship at larger at larger masses. Here, mass is kind of a strange thing to plot for these objects. So we're plotting luminosity, and you can see that these things do, in fact, follow this relationship. Just in comparison, the Milky Way globular clusters lie in sort of a scatter plot kind of along this whole region, and so don't have any sort of relationship. And so I think that's actually a fairly interesting piece of evidence that these objects are, in fact, galaxies as opposed to star clusters.
Where would Willman 1 be on?
Yeah, so just a sec, definitely. And so I haven't plotted some of the fainter ones. So Willman 1 kind of sits up about here. And so it's a slightly, but then, it's whether or not we got rid of those high metallicity stars in the sample, so things are a little bit complicated. It sits a bit higher, even getting rid of those high metallicity stars, than we would expect. The fact that these also lie on the mass, on a metallicity relationship, also argues against significant amounts of tidal stripping of the luminous component. So let's just hypothesize that galaxies form somewhere along this relationship, and you have a galaxy that, let's say, was much more luminous in the past. You would have fixed its metallicity. And if you then try and appeal to some sort of gravitational stripping to explain these low luminosities, you would get the wrong metallicity. And so I think this is a fairly interesting piece of evidence that these galaxies, these luminosities, these galaxies were born with the luminosities roughly that we're seeing today. And that's all I'm going to say about metallicity. Let's do tidal stripping in one last way. This is data for Ricardo Muniz, who was here last week, is working on and writing up. We now have very, very deep data of a handful of ultrafaint galaxies. And what we want to look for is evidence of tidal debris at very, very, very low surface brightnesses, so much below where the SDSS was measuring. So this is for Coma Berenices, one of the fainter of the ultrafaints. This is a very large area, so this is 2 degrees across. The Sloan discovery images are all within sort of 3 of those contours. I mean, you can see this is a very, very regular image, regular object down to very low surface brightnesses. And let me just explain what very low surface brightnesses are. This contour map was made with these red stars. This is the color magnitude diagram from the CFHT data. The SDSS limits are much higher. So this is the SDSS limits where this object were discovered are the stars that are up here. So we're going down about 3 magnitudes deeper, and we still see no evidence for tidal stripping. We are also hoping to do some IMF work with these data, which is also kind of interesting and exciting, but not relevant to the talk. So this object doesn't show evidence, at least in these data, for tidal stripping, and that is not true for Ursa Major 2. So another 40. Well, so yeah, 45 kilometers, 45 kiloparsecs. Ursa Major is again at 40. It's roughly at the same. So it's also at a similar distance as Willman. So in this case, we see some evidence for something fairly funky going on. So again, the SDSS image is all within this region. This is extending out almost a full degree. And so we don't have velocities in these extended regions to be able to say what's going on here. But this is evidence that something else is going on besides, or at least evidence that you might want to take some of the masses with a grain of salt. So, sort of in summary in terms of tidal interaction, while we do see evidence for a few, Willman 1 in this object, for tidal interactions, for the rest of them, and that's really the majority, we see no evidence for tidal interactions, which means that our masses are probably fairly solid. To within factors of 2 as is usual. And so really, again, in the absence of evidence, we assume that these stars are facially tracing the gravitational potential. So now I could actually get started on the interesting stuff, which is, I think, timed perfectly. So now that we believe the masses, we can use these to do a lot more things. And so, in the interest of this workshop and relevant to this workshop, the ultra-faint galaxies are extremely versatile probes for dark matter. And they're more versatile, certainly when I started in on these about 4 years ago. I had no, imagination or something to think that we were going to be able to do so much with these objects. And so what I'll go through is 3 different ways that these things are interesting. They're very good targets for indirect dark matter detection. This is something that's coming out of this workshop, is that they perhaps put some interesting constraints from their phase space densities. And they're also extremely interesting in terms of galaxy formation and small-scale structure fluctuations. And so I'll just go through these 3 slowly. And again, here's where discussion is welcome. Not that it wasn't before, but... So the indirect dark matter detection, and we have 2 experts we have lots of experts in the room. If the dark matter particle is some sort of SUSY particle, we would expect that there should be occasional annihilations between dark matter particles that would produce an observable signature, namely in gamma rays. And so this is a picture of the Milky Way, or sort of the all-sky, from Mike Coulin, that if we were able to see only dark matter, we would see something like this. So this is the galactic center booming right in the middle, and you can see various different satellites in this image. And so the galactic center is the place to really look for this signature. It has the highest dark matter densities, and so the highest probability for annihilation. It's also the closest. It's only 8 kiloparsecs away, whereas the closest dwarf galaxy is more like 20 to 30 kiloparsecs away. And so that really is the place to go and look for this signal. The problem is that the galactic center is kind of a mess and produces gamma rays in many different astrophysical ways. And so it would be very difficult to distinguish between this signal and something else. And so there's been some argument that you should look kind of just off the galactic center, with the idea being that looking just off, you'll still see the annihilation signal, but some of this astrophysics will go away, like not looking towards the galactic black hole and that sort of thing. The problem is twofold. One, the Fermi satellite, which is currently up and looking at things, is only really good for point sources and has more of trouble looking for diffuse emission. The other issue is that we don't know the potential of the galactic center, or the galactic potential off of the Milky Way fairly well. And so you have to understand what the flattening of the Milky Way halo is and a lot of other things. And so in some sense, the dwarf galaxies are worse because they're farther away and the signal is just lower. But they're better in the sense that they are clean sources. We don't expect any sort of intrinsic gamma rays from these objects. And so if you do see something, you have a fairly slam dunk in terms of what you're seeing. So usually at this point in the talk, I say, and it would be really cool if we could see it. So here are the detection thresholds from Louis Strigari. These have been updated, but this just gives you an idea. So if we know what the density profile of these dwarfs are, we have some model for the particle physics, we can predict what the gamma ray flux should be. So this is just a likelihood function, and this is flux, where this really is a sliding scale. I don't want to argue about the numbers. You can see Ursa Minor, which was one of the classical dwarfs, had the strongest predicted flux of the dwarfs up until the ultrafaints were discovered. And the ultrafaints, because they're a little bit closer, have a little bit higher predicted flux. And so there are, in fact, now results, which is really quite remarkable. So Tesla Geltima presented Fermi results from their 9-month data at a conference last week. So this is our favorite Segue 1. This is 5 degrees, so much bigger than the area that we were talking about before. And the red are individual counts. And there's nothing there. But there's some hope. And, it's possible that if you look at where all the dwarfs are and you stack these images, perhaps we'll be able to see some sort of signal. But it's amazing to be able to just show data for this since we've been talking about it for a while. In terms of constraints on dark matter particles, the dwarfs at the moment are these upper limits are sort of just nibbling at parameter space. They're not doing any real damage yet. So this is from Stefano as plotting the annihilation cross-section as a function of WIMP mass, where the sort of burnt orange are the favored models at the moment. The black and the red curves are the upper limits from the 9-month data, I believe, for Segue 1 and Ursa Minor. And you can see it's just sort of starting to eat into some of the interesting limits. So stay tuned there. Perhaps the 5-year data will actually start having lunch on the parameter space. So moving on to the phase space density constraints. And this is the slide that I sort of know the least about. This is something we've been talking about in the meeting just this week. So the idea here is that just the density of these galaxies gives you some constraint on the dark matter particle in the following sense. So we know for a collisionless system, the collisionless Boltzmann equation says that if you have some phase space density, that should be preserved. So you should not change phase space density pretty much no matter what you do. So if we set up, if you have some sort of hierarchical model and you can figure out what the phase space density in some dark matter halo was as it was formed, you should expect to see that phase space density today. Or at least you should see something that doesn't go up. So the problem here is that we measure something that's called the coarse-grained phase space density. That is, we're measuring stars that are discrete. They're not continuous, and that's where these numbers come from. So basically, we can put lower limits. I'm going to be a little dyslexic there. But if we see some phase space density, we know that the particle cannot actually have set up a phase space density lower than that. So the phase space can only go down. So if we see something, we know that there's some sort of upper limit there. The ultrafaints do, in fact, put an interesting constraint on, but the problem is sort of how you measure this parameter. So this quantity Q is defined as the density, which is really the central density of an object, divided by the velocity dispersion, but it's not the velocity dispersion of the stars, it's the dark matter. And so connecting those two, at first blush, is very easy, and we publish numbers. And now that we think about it a little bit more, it actually turns out to be a little bit more difficult to do that properly. And so that's why I'm not actually going to show any results here. From the theory, we expect for some sort of CDM model that Q should be very, very large, so something like 10 to the 11th or more in these units. If there's a warm dark matter particle, so this is a gravitino or a stereoneutrino, the numbers are more in the order, are 10 orders of magnitude smaller, something more like 10 to the minus 3, plus or minus a whole lot. And this was something that Kev sent to me last night. This is for a stereoneutrino, plotting Q max, so the observed Q max as a function of the particle mass. And I'm only just going to put some sort of fuzzy limits because we really need to think about this a lot more in detail, and we're going to do that tomorrow. The ultrafaints are sort of in this range, so between 10 to the minus 4 conservatively, perhaps as high as something like 10 to the minus 2, but really stay tuned there for any sort of limits. Okay, so the last bit of physics we can do with these objects is just trying to count up the number of them and compare to theory. So this is a missing satellite problem that I alluded to a long time ago. So this is in its simplest form, and this is what we published a couple years ago, the circular velocity as a function of just the cumulative number of satellites. So the lines is the Via Lactea simulations, and these are an old simulation. I think this is Via Lactea 1, but I may be wrong. No, these are, in fact, this is 1. And so here is the old missing satellite problem, where these are the dwarfs before 2005, when we didn't find the ultrafaints up at 11, and these numbers are very different. And the real thing to notice here is that the discrepancy between observations and the predictions increase as you go to lower masses, as you go to lower circular velocities. And so then adding in the dwarfs that we know, and this is adding in assuming a full coverage for the Sloan Digital Sky Survey, so something like 50 or 60 dwarfs. The numbers actually agree a little bit better. And so now instead of having a real missing satellite problem, it's becoming more of a missing satellite issue. And again, this is not this is not accounting for the incompleteness of Sloan as a function of radius. And so we really don't know how to do this incompleteness, because this is the test that we're really doing. And so, it's unclear what's going to happen as we go to deeper, probing deeper into the Milky Way. And so it's possible that these things may align. There probably will always be some discrepancy at the order of factor of 2, whereas there are going to be some dark matter halos that never form stars. I'll talk about that a bit in the next slide. So, this is now a missing satellite issue in this sense, but, we can now be a lot more sophisticated. So going back and looking at Louis' plot, this M300 plot, and thinking a little bit more about models, this is stuff that Risa presented just a couple days ago at one of the slams, I think. So this is a function of luminosity, M300. What do the galaxy formation models actually say? So that previous plot was just saying, here are the dark matter halos, and here's what we observe. But perhaps we can do this galaxy to dark matter halo mapping a little bit better. So here again is the same plot. The blue, or I guess that's like turquoise or something, are the data points. And the red and the blue are from two different galaxy formation models. And so this is from Michael Busha, who's Risa's graduate student, or postdoc, sorry, can really reproduce our M300 results from a fairly simple model of halo occupation. So she went through a couple days ago. The idea here is actually fairly simple. So you take all of the dark matter halos that are around the Milky Way, predicted around the Milky Way, as I was showing in the previous plot, and then you populate them with galaxies. And you do that based on this fairly simple prescription. You say, if a galaxy was formed before reionization and had a certain mass, you're allowed to have stars in it. If it formed after reionization, that threshold just gets a whole lot higher. And then you just sort of watch how those halos evolve in the n-body simulation, so you know what their final masses are. And this is what you predict. So that the M300 as a function of luminosity. Oh, sorry, there's one more piece here, is that you have to figure out some mapping between the halo mass and the luminosity. This is set on observations of the luminosity function at higher luminosities, just extrapolated down to fainter luminosities. And so this is what you predict, that the M300 is basically consistent with the observations, but does in fact predict a little bit of a slope. So perhaps, as we get more and more data, we'll be able to constrain this a little bit better. What's interesting now is that we have, for all of these theoretical points, we can go back and ask, what was the maximum size of that halo at any point? And it seems that the Milky Way satellites were all formed in dark matter halos that were something like 10 to the 9, but with a fairly large scatter, which, when we first started this out, I think, to me at least, is fairly surprising. So we're able to match at least the luminosity and the mass. What we're not able to match yet is the numbers and the radial distribution. And so this is my last point, is to say, how can we go forward? So clearly, getting better masses is one way to go forward. But to me, at least, being able to probe and look for galaxies farther into the Milky Way halo really is the way forward. And so currently, in current searches for these ultrafaint galaxies, we're only probing a very, very tiny amount of volume. So for the absolute faintest galaxies, we have to get down to the main sequence turnoff. And that corresponds for the Sloan Digital Sky Survey, which the limit is about 22 in R band. That corresponds to roughly, I I think I have a circle here, roughly 30 or 40 kiloparsecs. And so 30 or 40 kiloparsecs in a 400 kiloparsec Milky Way halo corresponds to an extremely small fraction of the probed volume. So that's for the SES-SDR7 is probing a remarkably small amount of volume. We want to be able to probe the full volume of the Milky Way for these faintest objects. And so there's a number of surveys coming online. Some of them are fantasy and some are not. So something like PanSTARRS or DES will certainly be able to probe a little bit more volume, both because they're being able to probe a little bit larger region and getting to deeper magnitudes. And it's really deeper magnitudes that's the key. And so something like LSST in one exposure will get you something like half of the volume or less. And the full LSST down to 27th magnitude should get you out to most of the way out to the virial radius of the Milky Way. And so, doing this is extremely difficult, but I think necessary to really constrain the Milky or the radial distribution of satellites and understand what the true number is. Is it 50 or is it 500? Those are very, very different numbers. So this is where a lot of effort is going in to try and find these things at much larger distances. And there's a whole cans and cans of worms as you go to fainter and fainter magnitudes in doing these searches. So just to conclude, the dwarfs really are extreme in every sense of the word. They're the least luminous galaxies, the highest mass to light ratios, and some of the most metal-poor systems that we know. They really are very good probes for dark matter in a number of different ways that I've gone through. And so I'll just leave you with this, and many of you have seen this before, but it's my favorite Google search I've ever done. And take questions. Thanks. Yep.
I guess the Segue one was saying, there's no here. In that picture, you say, well, you can't see. There's nothing that you can't see here in the galaxy anyway. And you're saying how you could, subtract off the stars and so on. But how would you even know in that field of view that there might be a galaxy? How would you know that you should even try to subtract off the stars? Just take them field of view and take out stars and say, oh, look, there's something faint in the background. Or how would you know to even do that?
So this is why all of the galaxies have been found in the Sloan. So, sure, it's just asking, how do you actually find these overdensities? How do you know where to look? And the answer is we have no idea. And so we do a huge grid search, both across the entire Sloan Digital Sky Survey, so that's now, I think, 8,000 square degrees or more. And we step through in distance. So we step through from 20 kiloparsecs out to 300 kiloparsecs. And just step through in grid as a function, within sort of every 5 arc minutes. And so this is why these galaxies have just been found, is that it takes a huge amount of computing power and disk space. So hopefully that will only get better.
So there's no reason to think that at the outset that particular field of view is going to
right.
contain.
And so the key then is, what is statistically overdense, and trying to set those thresholds is really where all of the where this game gets complicated. Joel?
Clearly, along the same lines, right at the beginning of your talk, you emphasized that you have effectively a surface brightness lower limit.
Yes.
And the question is, to what extent is this apparent constancy of the mass inside 300 parsecs a consequence of that cut that you're making, that so far you haven't been able to get down below a certain surface density? And could that also be the explanation for why the predicted slope in that diagram you've shown, the Pravtsev and the Busha doesn't seem to be reflected in the observations? It seem fairly flat. And
So I think
finally,
oh gosh, I'm not going to remember 3 questions.
well, the last part is the interesting one for you. Is there some way that you figured out that you could, maybe with the PanSTARRS data or other data that's coming in now, go to lower surface density, or is it really just too hard?
Well, I'll answer the one that I remember first. So I do think we can go to lower surface densities. And the reason we can do that, I think, is that we really understand the problem here is false positives. And so as you go to lower surface density, you're going to get higher number of false positives. And we're getting better and better at doing that. So the first...
Chemical abundance.
No, well, no, actually, just from statistical overdensities and getting smarter at how we subtract off the stellar background in these images. So, when we're doing the searches, we only have the imaging and that's it. So I think if we can better define the thresholds, we will be able to get down to lower to lower surface densities. Not a lot lower at this point, but maybe a little bit better. So to answer your question about the M300 plot, so the surface brightness is there. There's a range of surface brightness as well. And so I don't think that's introducing anything, especially if these stars, the stars are nothing in terms of the total mass of these objects. And so they should be tracing the potential fairly well. And so I don't see anything about surface brightness that should enter.
Objects that were intrinsically lower density, and that was the reason that they're lower surface brightness. They're just bigger halos.
It's possible. But, maybe we should have seen things that had lower.
Asking the question is that James Bullock told me that he thinks that that's what's going on.
I mean, I think Joel's point basically is that if you, in the context of these spherical models, if you fix the velocity dispersions of what's roughly observed, there's a little bit of dependency with the scale radius of the stellar system too. So if you find a system that has a velocity dispersion of 5 kilometers per second and it's a little bit more extended than these things are, then that's going to reduce the mass of the system. Like if you focus in the context of certain models.
And so we know that we are not, that we are biased, but it's not clear whether or not we're incomplete. And so to do that, we just have to do the search. And we are definitely, it's something that's on our list of things to do. Yeah.
Well, just follow up on that, probably for you, maybe probably for Risa as well. Do the models, the galaxy formation models, can they tell you anything about what the surface brightnesses might be, or is that just way beyond what you can reasonably predict? In other words,
They can barely do the luminosity.
Okay. But if you connect luminosity with side,
They don't make any prediction as to the size. That's the problem.
Yeah.
Yeah, I mean, if you combine it with some assumption about the size, then yes.
so you could build that in, but it wouldn't be very informative because it's based on what you built in. Okay.
I wouldn't entirely agree with that. I mean, we can't predict the size of it and agree with philosophy. Unless you're involved about the distribution of surface brightness that are in the current models, but if you can predict that, I don't think they're particularly robust for tendencies of the sun.
It would be interesting if you do predict a large population of low surface brightness things. It would just make us work harder to try and find them.
Why would they be less robust than the M300?
I mean, because you're.
From the simulation, you get the size of the halo from the simulation. You don't get the size of the halo. Yeah, but these things are totally dark.
And you don't get the size of the stellar component.
It's a standard thing that everybody does in SAM, so I can relate the size of the
Well,
model.
it's a simple calculation. The question is how accurate is it, right? I mean, if you know figuring out the angle of length with the galaxies, which is not as easy as it would be calculating that massive luminosity.
Yeah.
I was just going to say, you didn't really talk at all about the orbits of these satellites. So I think Sagittarius has a proper motion, but is
Yeah.
that the only one that does?
So of the classical dwarfs, there are orbits for a handful of those. Those are done with HST, and they have large error bars, but they do have orbits. We have, it's funny, these were not actually discovered in the, I guess they were just, we have a approved program to do proper motions for a handful of the ultrafaints. It's a very, very difficult measurement, but I think it's important enough that we have to do it. Really want to do 2 or 3 epochs of proper motions to really believe what's going on. For the ultrafaints, the question is, you have a background quasar, you have to image deep enough to have actually enough stars in the field to be able to do a decent measurement. There's just, they're so, the surface brightnesses are so low, you actually are running out of stars. And so that's where I think some of we'll do this. Pietek and Pryor, who are at Rutgers, are the ones that are really going to do the hard work.
You're just saying there's so few stars that actually getting the mean proper motion of the satellites.
Right, so there's 2 things, right? There's proper motion of the satellite itself to get its orbits. That I think we have a hope of doing, in the next 5 to 8 years. Getting the internal motions, proper motions of the dwarfs, that would be fantastic, because then we could start constraining the anisotropy and getting the density profiles. I think that's a fairly long ways off, at least for the ultrafaints. For the more dense satellites where there's a lot more stars, maybe it's possible, but it's tough.
Do you expect these? I mean, this is about the these things, so you did something like Seg 1, which is currently at 23 kiloparsecs. You said, what would you expect its barycenter might be?
Well, we have no idea what, but we see no evidence for. That's true. So very few of these. So one thing we did try and look at is, maybe we're seeing some ellipticity in these objects because they're at, apo or peri or something like that. And there's no correlation between the ellipticity and the galactocentric velocity. So something that's a galactocentric velocity of 0 is not preferentially elliptical or something along those lines. The error bars are all large there, and there's not that many objects. But cool. Thanks.